When hydraulic systems are designed, whether on paper or computer, the layout of the system is expressed in what is called a schematic. A schematic is a line drawing made up of a series of symbols and connections that represent the actual components in a hydraulic system. In this course, you will learn to identify basic schematic symbols. You'll also learn where they are placed in the schematic of a basic hydraulic system. Although there are dozens of different symbols used in a complex schematic drawing, it is important to be able to recognize several basic symbols.
Symbols are critical for technical communication. They are not dependent on any specific language, being international in scope and character. Hydraulic graphic symbols emphasize the function and methods of operation of components. These symbols can be rather simple to draw if we understand their logic and the elementary forms used in symbol design. The elementary forms of symbols are circles, squares, triangles, arcs, arrows, dots, and crosses. Click on each of the following categories to see how these common hydraulic graphic symbols are logically constructed, giving symbolic representation of its component. Lines. Understanding graphic line symbols is critical to proper interpretation of schematics. Continuous lines indicate a working line, pilot supply, return, or electrical line. A dashed line indicates a pilot, drain, purge, or bleed line. Flexible lines indicate a hose, usually connected to a moving part. Lines crossing may use loops at crossovers or be straight across. Lines joining may use a dot at the junction or at right angles. Reservoirs. Reservoirs that are vented are shown as a rectangle with the top line omitted. Pressurized reservoirs are shown as a capsule. Reservoirs may have fluid lines terminating above or below the fluid level. The above oil level return line terminates at or slightly below the upright legs of the tank symbol. The below oil line return line touches the bottom of the tank symbol. A simplified symbol to represent the reservoir minimizes the need to draw a number of lines returning to the reservoir. A number of these in the same circuit will represent a common reservoir. These symbols have the same function as the ground symbol in electric circuits. Rotary devices are shown as a circle. Pumps having an energy triangle pointing to the outside perimeter indicate the energy is leaving the component. A sloping arrow through the circle indicates that the pump is variable or the output flow can be regulated without changing shaft speed. A control symbol with an energy triangle that is connected to an adjustable spring indicates that the pump is pressure compensated. Some types of pumps have internal leakage that is returned to the tank by a case drain. This is indicated with a drain line drawn leaving the circle. Pumps that are bidirectional are shown with two energy flow triangles. The symbol for a flow control valve begins with an upper and lower arc. This would symbolize a fixed orifice. An arrow drawn sloping through the arcs indicate that the orifice is adjustable. This would be the graphic symbol for a needle valve. When we add an arrow to the flow line inside a control box, we have indicated that the valve is pressure compensated or true flow control. A flow control valve with a check valve indicates reverse flow around the valve. Directional control valves. The symbol for a directional control valve have multiple envelopes showing the number of positions the valve may have. A 3-position directional control valve is shown with 3 envelopes. Arrows in each envelope indicate the possible direction of flow while the valve is in that position. The center position in a 3-position directional control valve is designed according to the type of circuit or application. This centered position indicates the flow path of the fluid while the valve is centered. While there are many types of center configurations, the 4 most common are tandem, closed, float, and open. To shift the valve or activate it, we can use a mechanical handle or lever, an electric solenoid, or hydraulic pilot pressure. The springs indicate that the valve is centered when not activated. In position 1 or centered, fluid flows from the pump through the valve to the tank. This is a tandem center. When we shift the valve to position 2, fluid now flows from P to A, extending the cylinder, shifting to position 3, which shows flow now from P to B, and from A to T the cylinder retracts. Pressure valves. The symbol for a pressure valve begins with a single envelope. The arrow in the envelope depicts the direction of flow through the valve. The ports are indicated as 1 and 2, or primary and secondary. Flow through the valve is from the primary to the secondary port. Notice that in the normal position, the arrow is not aligned with the ports. This indicates that the valve is normally closed. All pressure valves are normally closed with the exception of a pressure-reducing valve, which is normally open. The spring located perpendicular to the arrow indicates that the spring force holds the valve closed. An arrow diagonally through the spring indicates that the spring force is adjustable. Pilot pressure opposes spring force. This is indicated by the dotted line running from the primary port perpendicular to the arrow opposite the spring. When the hydraulic pressure piloted from the primary port exceeds the force of the spring, the valve moves to the open position, aligning the primary and secondary ports. Check valves. Check valve symbols are drawn with a small circle inside an open triangle. Free flow is opposite the direction the triangle is pointed. As the circle moves into the triangle, the flow is blocked or checked. Check valves may be piloted to open or to close. Pilot to open is indicated with a pilot line directed to the triangle shown to push the circle away from the seal. Pilot to close is indicated by directing the pilot line to back of the circle or into the seat. Motors. Hydraulic motor graphic symbols are opposite of hydraulic pumps. Their difference being the energy triangle points into the circle indicating fluid energy entering. Two energy triangles pointing in indicate a bidirectional or reversible motor. As with pumps, many hydraulic motor designs have internal leakage. A dotted line leaving the circle indicates a drain line to the tank. Cylinders. Fluid power cylinders with no unusual relationship between the bore and rod size are shown. Single acting, double acting, and double rod. An integral rectangle adjacent to the symbol for the piston indicates a cushion device at the end of the stroke. If the diameter of the rod is larger than usual for the bore size, the symbol must reflect this. Filters. The graphic symbol for a hydraulic fluid condition device is shown with a square standing on end. A dotted line across opposite corners indicates that it is a filter or strainer. Adding a check valve across and parallel to the ports indicate that the filter has a bypass. Heat exchanger. Hydraulic heat exchangers may be considered coolers or heaters. Their graphic symbols are often confused. As with a filter, the base symbol is shown as a square on end. Arrows pointing in indicate the introduction of heat or a heater. Arrows pointing out indicate heat dissipating or a cooler. Arrows pointing in and out would indicate a temperature controller or temperature that is maintained between two predetermined limits. In this learning lab, you will learn the proper name. A schematic is a compilation of graphic symbols interconnected, showing a sequence of operational flow. In short, they explain how a circuit functions. Correct schematic reading is the most important element of hydraulic troubleshooting. Although initially most circuits may appear complicated, recognizing standard symbols and systematic flow tracing simplifies the process. This circuit uses two sequence valves. They are normally closed valves that open at a predetermined setting. By tracing the flow in this circuit, we should be able to determine how this circuit is designed to operate. This process is called reading a schematic. Let's begin at the pump. Follow the flow past the relief valve to the directional control valve, which is shifted to the upper position as shown. The directional control valve directs flow to the lines in the upper circuit. Here, flow can go three places. The upper check valve blocks one passage. The closed sequence valve blocks another. But flow to the A port of the actuator is open. As the cylinder rod retracts, flow from the B port is blocked at the check valve, so it exits to the tank through the directional control valve. When the cylinder is fully retracted, pressure will build in the pilot passage of the sequence valve. It opens and sends pilot pressure to the directional control valve. Pilot pressure on the upper side of the directional control valve will shift the valve downward. Pump flow is now directed to the lower circuit, and the flow here goes to 3 places. It is blocked at the check valve and blocked at the closed sequence valve. But flow to the B port of the actuator is open. Flow in the port will apply pressure to the piston and extend the cylinder. Flow out of the A port is blocked by the upper check valve, so it flows through the directional control valve to the tank. When the cylinder is fully extended, pressure continues to build. Pilot pressure opens the sequence valve on the bottom. This sends pilot pressure to the lower side of the directional control valve, shifting it back into the upper position. Now, pump flow is once again directed to the rod side of the actuator to retract the cylinder, and the cycle begins once again. Tracing the flow in this circuit reveals that it is designed to keep retracting and extending automatically. Now that we understand the circuit, we may conclude that the proper function of the system will depend on the proper setting and function of the sequence valves, and the proper function of the hydraulically piloted directional control valve. This is a high-low circuit. Such a circuit would be used to achieve high speed or rapid advance at low pressure, followed by slow speed and high force. A good example of a high-low system would be a press, where the ram would rapidly advance up to the workpiece. At that time, the pressure starts to build. The flow from the high-volume pump is diverted to the tank. The low-volume pump would produce the little flow needed to continue moving the ram into the workpiece. The pressure will continue to rise until it reaches the relief valve setting. When the directional control valve is reversed, the pressure drops and the unloading valve closes. The cylinder would retract at a rapid speed. Now let's examine more closely the components that make up this system. First, the unloading valve. This valve has been set at 500 psi. When the system pressure reaches 500 psi, this valve will open and allow the flow from the high-volume pump to go back to the tank at minimal pressure. Next, we will look at the function of the check valve. When the system pressure is less than the unloading valve setting, flow from the high-volume pump flows through the check valve to combine with the flow from the low-volume pump. After the unloading valve opens, this check valve closes so that the flow from the low-volume pump won't flow to the unloading valve. Now, let's take a look at the high-low pump group. This is a double pump. These pumps have a common inlet and separate outlets. During low-pressure rapid advance, both pump flows are combined. When the unloading valve opens, the large pump's flow returns to the tank, and the small pump's flow is used to do the work. Finally, we will look at the system pressure relief valve. This valve limits the maximum system pressure. Notice the schematic shows the pressure at which the valve should be set. Now, watch as these components work. In our circuit, the cylinder has a weight that would cause it to free fall or drop at an uncontrolled rate. A counterbalance valve is placed in the rod end port of the cylinder to apply back pressure. The back pressure is the result of the load trying to force the fluid out of the cylinder and through the counterbalance valve, which is closed. The counterbalance valve has to be set slightly above the load-induced pressure. When shifted, the directional control valve applies pressure on the cylinder piston. This, in turn, increases the back pressure, causing the counterbalance valve to open, allowing the cylinder to lower the load at a controlled rate. Now let's examine more closely the components that make up this system. First, we'll look at the offline or kidney loop filter circuit. This circuit consists of a pump motor group, a filter, and an air-to-oil heat exchanger. The pump draws hydraulic fluid from the reservoir, passing the fluid through a filter and an air-to-oil heat exchanger. This circuit usually runs continually to keep the hydraulic fluid clean and cool. Next, is the pressure compensated pump. The pressure compensated pump de-strokes when the directional control valve is centered. At this time, there is pressure being maintained between the pump and directional control valve, but no flow. When the directional control valve is shifted, the pump goes on stroke, providing flow for the circuit. Next, we have the directional control valve. This is a 3-position, 4-way valve with a float center. This valve, when centered, will block flow from the pump so that pressure will build and de-stroke the pump. Both work ports are routed back to the tank, so there is no pressure in the work port lines, except between the rod end of the cylinder and the counterbalance valve. Now, we look at the counterbalance valve. The counterbalance valve maintains back pressure on the rod side of the cylinder so that the cylinder brings the load down at a controlled rate of speed. The check valve is used to lock and hold the load on this cylinder when the directional control valve is centered. Now, let's watch the system work again and see how each component operates.